So the second session, also colored stones and pearls. And our first speaker is going to talk to us about Cobalt Spinel. It's being presented by Dr. Aaron Palke, who is the Senior Research Scientist at GIA. Aaron?
Thank you, Shane. I didn't actually know I was leading the session until a few minutes ago because I wasn't paying attention, but I'm happy to start everybody off with some talk about blue spinel and some sort of nomenclatural issues in gemology, and some kind of more in-depth discussion of some technical color science as well. So, like Shane said, we're talking about spinel, and specifically, we want to get at this kind of term that the trade uses, cobalt spinel, for bright, vivid, saturated blue spinels that we see in the trade colored by cobalt. And it's been known for a long time that cobalt is actually a very strong chromophore in spinel. And you typically see cobalt spinels typically associated with synthetics, right? Because the synthetic growers know that they can add cobalt to their spinels and get really bright, vivid, desirable colors, blue colors, in their synthetic material. However, it is known as well that in some deposits around the world, nature does produce some bright, vivid blue spinels as well that are also strongly colored by cobalt. Like, for instance, the deposits in Lucia and Vietnam produce very spectacular, vivid cobalt blue spinels with quite a bit of cobalt in them, oftentimes up to several hundred ppm cobalt. But nature also produces some different kinds of blue spinels as well, with colors that are not as bright and vivid and not as desirable. So this brings up the question of what is a cobalt spinel. We're going to start here. So this is a visible absorption spectrum of a cobalt spinel from Lucia in Vietnam. It's got about 550 ppm cobalt. And so what we're looking at here, this is a spectrum showing how much of the visible light is absorbed at every single wavelength. So we're going from 400 nanometers, 400 nanometers with the blue-violet light up to 700 nanometers with the red light. And we can see the main features. If you've seen this many visible absorption spectra of colored stones, you've probably seen a spectrum like this. This is a typical cobalt spectrum. Three major features, around 550, 580, and about 630 nanometers. And this absorption, so this is showing that the light in this region is being heavily absorbed, and where there's little absorption, this is where all the light goes through the stone and comes to our eyes. So we're sucking up most of the green, yellow, orange, red light, and we're letting all this blue light come through. And if you've done a lot of gemology, you're more familiar with this probably. This is what you would see through a spectroscope for a cobalt spinel. You have these three main features here, and this is how you would typically identify cobalt in a spinel like this. And here's the actual spinel that the spectrum was taken from. This was polished into a plate, so a double-side polished wafer, in order to get a good spectroscopy analysis on it. And if we can take this spectrum and run it through a series of calculations and calculate exactly what the color of this spectrum would produce in a 1 millimeter path length stone. And so that's shown here. And this is important. We're going to come back to this later. So we can actually use this spectrum and get at calculate the color we would see in a spinel at various different cobalt concentrations, and get some idea of what exactly is a cobalt spinel, and where do you make this cutoff of how much cobalt do you need in order to apply this terminology of cobalt spinel. So again, this is the question: what is a cobalt spinel? Like I said, it's about a quality of color. So cobalt spinel is really bright, vivid blue spinels. And of course, it's a cobalt spinel, so it has to be colored by cobalt. But how much is enough? So how much cobalt do you have in this stone, which is a darker, less saturated spinel? Still a nice blue. I mean, it's a fairly attractive stone, but how much cobalt do you have to have before you can take your spinel from this into this nice, vivid cobalt spinel that we see on the left? And this is really sort of the problem here, is almost all spinel will have some concentration of cobalt, whether it's at the 1 parts per million level or the 500 parts per million level. And the problem goes even further in that In our lab, in the Gemological Institute of America, we have a laser ablation ICP-MS instrument, which we use to do chemical analyses on stones that come through the lab. And we can get, with our laser ablation ICP-MS, is very sensitive for trace elements like cobalt. We can detect down to about 0.2 parts per million cobalt. So let's ask the question. If we had a stone that came in, we could detect 0.2 parts per million cobalt. What would the color be in that stone? Let's imagine a well-proportioned, round, brilliant spinel. If that stone is about 1 carat, on average, the path length through that stone is going to be about 7.7 parts per million, 7.7 millimeters path length. So if we took that spectrum before from Lucian, Vietnam, we divide that spectrum to get 0.2 parts per million cobalt, and we then scale it to a 7.7 millimeter path length. We can calculate the color produced in that case, and it would be what you see in this box here. So basically, that amount of cobalt is producing absolutely no color in the stone. So even though there's some cobalt there, and it's absorbing some visible light, clearly that's not enough. So how much cobalt is enough? Well, the stone before I showed you 550 parts per million cobalt, that one was clearly a Cobalt Spinel. So right now, the answer we have is somewhere between 0.2 and 550 parts per million cobalt. But let's try to refine that a little bit. So what I'm showing here is a table with calculated colors for varying cobalt concentration from 5 to 50 parts per million cobalt, which I calculated using that spinel from Lucian, Vietnam. And going down, we have varying path lengths from 7.7 to 15.4 millimeters, which approximately correlates to stones from 1 to 8 carats. So we can see right away, at 5 parts per million cobalt, even the largest stones we're likely to see in the lab, 5 parts per million cobalt is not going to be enough to produce a nice, vivid blue saturated color in a spinel. However, at 50 parts per million cobalt, we can see even at a relatively small stone of 1 carat, a 7.7 millimeter path length, that's probably going to be enough cobalt in there. And even at the longer path lengths, this is still producing good color to enable us to call this type of a stone a Cobalt Spinel. At about 20 parts per million at the shorter path lengths, that's probably not going to be enough to really enable us to call this as a Cobalt Spinel. But as the path length starts increasing, you can start to see that 20 parts per million in some cases would be enough cobalt to produce enough color for us to call it a Cobalt Spinel. And so if we had to draw a boundary roughly, it would probably be somewhere around here. So your spinel is going to have about 20 to 50 parts per million cobalt at least, depending on the size of the stone, in order for it to qualify as a Cobalt Spinel. But it gets a little more complicated than that, because we've only considered cobalt in that case. But it's well known that there are other chromophores in blue spinels that contribute to the color and can degrade the color you get from the cobalt. And so that things like iron start to muddle things up. So this is a blue spinel from Tunduru, Tanzania. It's got 10 parts per million cobalt, so probably not enough even at that level to qualify as a Cobalt Spinel. But we can see in addition, it's got 22,000 parts per million iron. So it's got quite a bit of iron in there. And typically, when we have a lot of iron in your spinel, it starts to produce these steely gray blue colors that start to muddle things up and make the stone a little darker in tone, a little less attractive. And this is the spectrum, visible absorption spectrum we see for this stone. You can see there is some cobalt in there. There's clearly a cobalt contribution. And we can look at this a little more carefully. We can expand the x-axis to longer wavelengths. So we have some of the near-infrared shown in this spectrum as well. You're not going to see colors in this zone, but it helps us understand what these absorptions are going on here. When we look at it at this scale, we see these two big broad absorption bands at about 670 and 910 nanometers. This is likely octahedral iron 2+. And we can make that assignment tentatively based on comparisons with other known minerals that have octahedral iron 2+. We still have, like I said, we still have some cobalt contribution though right in here. But it gets even more complicated if we look at even more stones. So this is another blue spinel from Madagascar. It's got about 14 parts per million cobalt, which you can clearly see in this spectrum here. And it's got 7 parts per million iron. So it's got less iron than the previous stone. And what we can do is we can take 14 parts per million cobalt and actually calculate the absorption that we would see from that amount of cobalt in this stone, shown right here in the blue. And now what we do next is we can take that cobalt absorption and subtract it from the full spectrum. And we're left with this residual spectrum here in the red. And this is clearly different from that iron absorption we saw in the previous slide. If we look at it on its own, we see for the most part, there's 3 distinct absorption bands between about 500 and 600 nanometers. There's a sloping absorption as you go up to the blue, but the main features are these 3 absorption features here. And if we calculate the color from this spectrum, it's actually this kind of a nice pinkish color here. We're hypothesizing at this point that this is likely due to tetrahedral iron 3+. And for the most part, we're making that assumption because we've already identified the octahedral iron 2+ spectrum. We know that tetrahedral iron 2+ absorbs far out here in the infrared at about 2,000 nanometers. And we know the spectrum of octahedral iron 3+ is 2 strong bands around 450 and 2 more broad bands around 600 and 800 nanometers. And we just don't see those here. So we're thinking that this is likely, basically the only possibility left for Spinel, which only has tetrahedral and octahedral sites. The only possibility left is really tetrahedral iron 3+, because there's no other chromophores present in this stone at any appreciable levels. And this is a ubiquitous feature of many blue Spinels. In particular, the Spinels, blue Spinels that show a color change, so a difference in their color appearance between incandescent light and daylight. So it's like this stone shown here. In daylight, it's more of a blue color, and in incandescent light, in warmer light, it has more of a violet purplish color to it. And in all of these color change Spinels, this feature that we're calling tetrahedral iron 3+ shows up at about 550. There's a peak here, and there's a definite component of every color change Spinel that we've seen so far. And what's really going on here is it's the interplay between cobalt and this tetrahedral iron 3+ absorption that's causing this color change. So we have the visible light spectrum shown here from 400 to 700 nanometers. In cobalt, you have this clear, big transmission window, we call it, in the blue. But as we add this iron spectrum into it, we start to absorb some of that blue transmission window. You start closing that transmission window for the blue, which makes this small transmission window in the red relatively more important. And so we can get these nice color change Spinels when you combine these 2 chromophores, because it produces these 2 transmission windows that are accentuated, the blue accentuated in daylight equivalent light, cooler light, and the red transmission window accentuated in warmer incandescent light. So we've explored chromophore space for blue Spinels pretty well by now. Let's get back to the original question we had, which is, what is a Cobalt Spinel? And what criteria do we use to identify Cobalt Spinels? So as I mentioned earlier, a lot of this is really a color call. So Cobalt Spinel is defined by the color of the Spinel. It has to have a vivid, saturated blue color, and it should be reminiscent of synthetic blue Spinels that you see on the market, or some of the fine Spinels from Lucien, Vietnam. And of course, it's Cobalt Spinel, so it has to be colored by cobalt dominantly. Now, that's still pretty vague, I realize that. So let's go through some examples. Here is a Spinel. Oops. Here is a Spinel shown here. It's got a nice, bright, vivid, saturated blue color. It's got 46 parts per million cobalt. So as we mentioned earlier, 46 parts per million cobalt should be enough for this to be qualified as a Cobalt Spinel. We see in the absorption spectrum, the dominant feature are these cobalt peaks here. We see a little bit of an absorption from the iron, octahedral iron 2+, going into the red and the near infrared. But dominantly, the spectrum is dominated by cobalt. So this stone is okay for Cobalt Spinel. And you see here, it's got about 10,000 parts per million iron. Now, let's compare that with this next stone. This one has about 39 parts per million cobalt. So that should be enough to be able to produce enough cobalt color in this Spinel to qualify as a Cobalt Spinel. But it's got about 15,000 parts per million iron, so a lot more iron than that previous stone we saw. And you can see that in the spectrum as well. We have the cobalt absorption peaks shown very clearly here. But compared to the previous spectrum, it's got much more of this sloping absorption due to these octahedral iron 2+ absorption peaks. And so this stone, and you can see in the picture, it's got a much darker tone than the previous stone we showed. Even though it's a blue color, it's got a much darker tone. And so this Spinel would not qualify as a Cobalt Spinel due to the amount of cobalt it has, but also due to the concentration of iron in this stone. There's simply too much iron for this to be a Cobalt Spinel. And we can look at this a little further. So we can take this spectrum, we can calculate the cobalt contribution to the absorption spectrum. We can calculate the color produced by the entire spectrum, which is shown here. It's a pretty good match to the stone in the picture. And we can calculate how much color is produced by cobalt. And that's a nice color, right? That would be a nice color for a cobalt spinel, probably. But if we subtract the cobalt contribution from the overall spectrum, we're left with this gray spectrum, the residual spectrum here, which is the iron chromophores in this stone. And if we calculate the color produced by the iron in this stone, it's this dark gray color here. And so this is really what disqualifies this stone from being a cobalt spinel. It's got this dark gray color coming in from the iron contribution, which is causing the tone of this blue color to be a little too dark for it to qualify as a cobalt spinel. And let's compare these two stones. So we have the cobalt spinel and the non-cobalt spinel. Similar concentrations of cobalt, and you can see that in the spectrum. They both have a pretty clear cobalt absorption spectrum here. But the darker stone shown on the top has these big broad absorption bands coming in here, absorbing a lot of that light and giving an overall grayish cast, darkening the tone of this stone. And so really, it's not just about the cobalt in the stones. It's about the relative amounts of the cobalt and the iron in this stone that's causing one spinel to be a cobalt spinel and one to be an ordinary blue spinel. So to wrap this up a little bit, what is a cobalt spinel after all? We're still working on sort of developing our criteria exactly, but some of these things that we've identified here, the overall concentration of cobalt, the cobalt absorption spectrum, and the color are really what we should be used to identify cobalt spinel and make this cutoff between what is a cobalt spinel and what is not. So we must have about 20 to 50 parts per million cobalt, depending on the size of the stone. But also you must have a cobalt color, of course. And this is really the most important part of this, is the color that's really driving the call between cobalt spinel and non-cobalt spinel. And as I showed in the previous slide, even in these stones that are not cobalt spinel, the blue color is dominantly coming from the cobalt. And most of the spinels I've analyzed to date, the blue spinels I've analyzed to date, the cobalt is really the source of the blue color. And the iron is coming in and producing this grayish or kind of, in some cases, pinkish cast to the stones and taking it away from being a cobalt spinel. So we have to also look at the iron concentration of these stones. And there's some relationship between the amount of iron in the stones and the amount of cobalt in the stones. That can help us guide ourselves to this call, to make consistent calls between cobalt and non-cobalt spinel. So that's all I've got, and if you guys have any questions, I'd be happy to answer them.
Thank you, Aaron. Please, questions.
I don't know if this is a question or a comment. So, based on your presentation, I can understand that the presence of iron is going to help you decide whether you're going to call something a cobalt spinel or not. But it makes me look at other gemstones. Like, for example, cuprian tourmaline. You're calling a cuprian tourmaline, not you, but labs, because of the presence of copper. The presence of other elements in it is not stopping you from calling it a cuprian tourmaline. So help me understand why, in this situation, it's different.
And that's true. And so, like I showed in some of the previous slides, the blue color is basically only coming from the cobalt, and the iron is not producing blue. It's producing gray or sometimes pink. So this is a bit of a tricky question, sure. And I would agree with you. In cuprian tourmaline is whether or not copper is producing color. But we're trying to make our color calls a bit consistent with the way these terms are used in the trade. And so the way this term is used in the trade, it's used to denote these bright, vivid, saturated blue colors. And it's not used so much for the darker blue colors. And so the trade itself is using it in this sort of a way. So we're trying to develop some criteria we can use in the lab to help us make our color calls more consistent with what the trade is expecting for our reports that we put out on blue spinels.
Yes.
So it seems to me that it's more about ratio than...
That's actually a very good point, and that's something we're really looking into right now is, can you look at a ratio of iron and cobalt to guide us to make the right call on these stones. So that wouldn't be the only thing we would look at. We would also have to look at the color, of course, and the spectrum, but that's actually a really good point, and that's something we are looking into using potentially.
Yes, sir.
Are there any known treatments to create the cobalt color?
We have seen diffusion, yeah, in some spinels. We've seen people diffusing cobalt, but it's very thin rind of color around the stone. It doesn't go very deep. So it's not like beryllium diffusion of sapphires where you can really give a good body color to the stone, but it's we have seen some diffused spinels, yeah.
Back here.
Do we have a tolerance level for the amount of iron in the system? Like, because when you said it's 15,000, it's not acceptable to be calling cobalt. But at 10,000, you were calling it a cobalt. Do we have a minimum or a maximum limit?
We think it's probably not so much the minimum and maximum of iron, but it's like the previous questioner said, it may be more of a ratio between iron and cobalt. So even if you had a lot of iron, and like we showed, there's varying types of iron, that absorption spectra that you can have in your stone. So the total amount of iron may not be the best indicator, but maybe looking at like the ratios would be more helpful.
Okay, thank you very much, Aaron. We're going to have to move on.